I'm Ethan, my teammates are Chad and Fayyaz, and this is our capstone project, RIDAR. In the US in 2019, there were over 40,000 bicycle accidents with motor vehicles resulting in over 800 deaths. A large number of bicycle accidents occur because motorists fail to yield or see a bicyclist and end up colliding with them. While there are many safety systems bicyclists use to improve their visibility, such as lights and reflectors, vehicles still cause many accidents with bicyclists. The goal of our system is to use a LiDAR and a camera to detect cars approaching cyclists outside their field of vision to improve their situational awareness. Specifically, we will use an object detection algorithm to detect cars from the camera's input and then use LiDAR to determine how far away the cars are. From this, we can determine the danger of the situation and alert the user with visual warnings through a pair of heads-up display glasses. We need a sweeping LiDAR sensor with at least a 120-degree field of view and as much range as possible to be able to detect approaching cars at a far enough distance. For example, a car approaching at 30 miles per hour will travel 44 feet per second, so it is imperative that the LiDAR has the maximum range possible. One constraint with our project is finding sensors that will work within our budget. Specifically, there are a few LiDAR sensors that could work within our budget, but they can become expensive. In our case, the average LiDAR with a sufficient field of view within our budget has around 12 meters of range, or about 40 feet. For the sake of our project, we will be implementing and testing our system to detect cars using LiDAR within 12 meters as a proof of concept, knowing that in an actual application, we can easily extend the system to detect cars at a farther distance using a stronger LiDAR system. We need to have a camera with at least an 120-degree field of view to be able to identify cars within a wide field of view behind the biker. Additionally, we want to be able to detect a car using an object recognition algorithm with a less than 10% error rate. While we recognize that achieving 100% accuracy in detecting cars is not always feasible, we want our system to be as reliable as possible as it concerns human safety. This is the camera we were originally going to use, which had a field of view of 120 degrees. However, due to issues integrating this specific camera with the object detection algorithm, we had to switch to a different camera. The camera we were able to integrate only has a 75-degree field of view, but for the sake of our project, it is sufficient as a proof of concept. This is a block diagram representing our system. We have a Microsoft webcam working in tangent with the RP LiDAR sensor. The communication between different components is handled mostly using ROS. The camera is responsible for providing live camera footage to the YOLO V4 object detection algorithm we have implemented. From here, the coordinates of the bounding boxes that map out detected cars and people will be written to a TXT file where the ROS publisher node will read from the file and publish the coordinates to a ROS subscriber node. This subscriber node also receives data from the LiDAR. Then the algorithm will use both the data from the camera and the LiDAR to map up the obstacles behind the user and send over data for Tkinter to draw out on a canvas. This canvas will be displayed on the user's glasses. This is a video of the YOLO V4 object detection algorithm working. In the video, it is successfully detecting the presence of a person in the image. The coordinates of the bounding boxes drawn are used to calculate the angle at which to range the object using the LiDAR. Due to environmental limitations in the lab, we were unable to test the object detection algorithm working on real cars. Therefore, as an initial test, we used printouts of cars and showed them in front of the camera. Later, once we were able to mobilize our system, we would test on real cars. In this picture, you can see the YOLO algorithm successfully detecting cars. However, it was only able to detect the picture of the car if the picture was very close to the camera. This is likely due to the scale of the car in the photo being much different from the scale of the car relative to other objects in a real-world scenario. This video shows the full system working together to identify people and cars, and use the LiDAR to determine the ranged objects. The people are represented as yellow circles, and the red squares represent cars. You can see the system successfully recognizing both me and Chad as yellow circles, as well as the car represented by a yellow square. The system also picked up another person working in the lab behind us during this test. The system only displays the objects to the user if the camera detects a car or a person. Therefore, even if there is an inanimate object in front of the LiDAR, such as a chair, it will not erroneously warn the user. Here is another test of the system. It shows 3 people detected in the frame, as well as the picture of the car once it gets close enough to the camera. In an actual application, the visual would be displayed on a pair of augmented reality glasses so that the user can see this information without blocking their field of view. However, obtaining augmented reality glasses was too expensive for our budget, so we tested with a pair of glasses which has a small display built in front of the lens. While this type of heads-up display obstructs the user's view and is not ideal for a real-world scenario, It is sufficient for the proof of concept of our system. Initially, it was hard for us to test with cars in the current environment. We were unable to mobilize our system, so we decided to test with people and pictures of cars in the lab as a proof of concept. Later, when we obtained a power source that we could take outside of the lab, we were able to test on real cars. Here are the results when testing both the accuracy and latency of our system. You can see an example of the system seeing us and displaying us on the HUD accordingly. When using images of cars, we found that pictures were much less accurate as they were scaled down. Even though the accuracy was not 100%, the algorithm almost always was able to detect the object in the image. The tiny YOLO V4 algorithm took around 0.4 seconds to display the object detection. This was done through timers on the system checking before and after an object was detected. This was about 0.1 seconds off on what we intended to implement, but given better hardware, we would have been able to meet this requirement. The GUI display and the other parts of the system added about 0.03 seconds of latency, but this was negligible compared to the object detection. This video shows our system accurately detecting cars in a parking lot. There were 3 cars in front of us, and as Chad panned the system, we can see the different cars come into view. We developed a 3D model of the physical design that would house the components of our system. However, we did not have time to fabricate the design, so for testing purposes, we improvised a box to house the components that we could take outside. We also tested on cars driving by. In this test, a car drives down the road past us. The algorithm is able to successfully detect the car, but there are a few issues. The first issue is that the LiDAR that we are using is a cheap LiDAR which is not rated for outside use. Since it was cloudy outside, we were able to get somewhat reliable results, but when it was sunny, the sunlight would interfere with the LiDAR readings. Additionally, our hardware is not powerful enough to run the object detection algorithm at sufficient speed. The detection algorithm only runs at about 2.5 frames per second, so it is difficult to reliably track fast-moving objects. Sometimes, when the object gets close to the camera, the YOLO algorithm draws multiple bounding boxes around different parts of the same object, which results in multiple red squares being displayed, even though there is only one car. In the future, we could test filtering out overlapping bounding boxes to just create one cohesive box.